Good morning friends. Today we will be taking up some problems. We will have a tutorial session today on some of the problems based on the theory that we have covered already in first year class or in the last few days. So, let us take the first one, a very simple one. You are having a voltage source of 10 volts connected through a resistor 2 ohms, this is 1 ohm, then again you are having another source 5 volts, then 2 ohms, 6 ohms and a current source at this end of 4 amperes. All these values are in ohms 2, 1, 2, 6 and there are 3 sources. You are asked to calculate all the currents through different branches, all the currents in all the branches and the potential at nodes, say this node I call it B and C, all the currents and node potential V B and V C with respect to a reference, say this one. There has to be a reference whenever we specify the voltage of any particular node. Now, the easiest one will be to apply nodal equations at these nodes. So, if you apply nodal equation at B, at node B, what shall I write? Suppose this is the current I 1, this is the current I 2 and this is the current I 3, all going inward towards the point B. It could have been taken otherwise also, could have been taken away from B. So, at node B I 1 will be 10 minus V B by 2, it is flowing towards B, 10 minus V B by 2 plus this is with respect to the ground 5 volts. So, 5 minus V B by 1 plus V C minus V B by 2 and that is equal to 0. So, if you simplify, multiply by 2 and say if I multiply by 2, this will become 10 minus V B, this will be 10 minus twice V B. So, minus thrice V B and again one more. So, 4 V B. So, 4 V B minus V C is equal to 20. After simplifying this. Now, if I apply the same nodal equation at node C, what would be the currents? Once again, if I take currents going inward or say I 4 is going this way, suppose I 4 is the current going away from this. So, I 4 plus I 2 is equal to 4. Correct me if there is any slip. I 2 plus I 4 is equal to 4, is that agreed? And how much is I 2? V C minus V B by 2, thank you, and I 4 is V C by 6. So, that gives me finally 4 V C minus 3 V B is equal to 24, is it not? Just multiply by 6, 6 into 4, 24 and manipulation here gives me 3 V C plus 1 V C, 4 V C minus 3 V B. So, if you solve these two equations, you get equations are 4 VB minus VC, 4 VC minus 3 VB. So, you can multiply this by 4, add with this. So, 4 into 4 16 minus 3 and 4 into 20 plus 24. So, after doing that 104 divided by 13. So, that gives me 8. VC is equal to 12 and VB is equal to 8. Okay. So, what will be I1? Once you know VB and VC, you just use this one, that will give you I1 10 minus VB. Therefore, I1 will be 10 minus 8 by 2, is it not? This is 10, this is 8 divided by 2, okay. That is equal to 1 ampere. Similarly, I2 will be 12 minus 8 by 2. This is 12 minus 8 by 2. We have already got these values. So, this is 2 ampere. I3, similarly, I3 is this one 5 minus 8 divided by 1. This is at a higher potential 8. So, minus 3 ampere. Is that all right? This is at a potential of 8 volts, this is 5. So, current will be in this direction, and I4 similarly will be 2 ampere, 12 divided by 6. Okay. Let us take another example. Say this is the problem that we just now discussed, is based on simple nodal equations. We will take up a problem on maximum power transfer theorem, which you have studied in first year class. You are having a source of say 100 volts, a voltage source of 100 volts. You are having an impedance at the load end RL plus JXL, which is variable, and there is a reactance plus J 15 ohms. Okay. There are 3 conditions under which you are asked to calculate the condition for maximum power transfer. A, for RL is equal to 10, find P max. That means you are varying only XL. RL is fixed, only XL is varied. What will be the value of the maximum power that you can get here? Find P max and corresponding XL, okay, for this maximum power condition. Second condition is for XL equal to minus J 10 ohms. That means you are keeping the reactance of the load fixed, minus J 10 ohm. That means a capacitive reactance you have fixed. What will be the value of P max? When I say P max means load power, okay, this is P, and the corresponding value of RL, okay, this RL means corresponding to this maximum power. And thirdly, when both RL and XL are varied, okay, what will be P max and corresponding RL XL. Okay. So, the problem has got 3 sections, 3 different situations. So, let us take the first one. Before we go to attack this problem, we can think of reducing this parallel combination into a single R plus Jx form. So, what would be the value of this? I can reduce this network to a source and how much is this R? I will call it Ri and Jxi. So, how much is that? Ri plus Jxi will be the parallel combination of 10 ohms in parallel with J 15 ohms. Okay. That is 10 into J 15 divided by 10 plus J 15. Okay. You can take out 5. So, 2 into 15 30, J can be shown by an angle 90. This is 2 plus J 3. Okay. I will make very approximate calculations and simultaneously I will tell you how to make simple computations without using a calculator. How much is 2 plus J 3? 2 squared plus 3 squared 13 and 13. So, square root of 13 and an angle of tan inverse 3 by 2, tan inverse 1.5. How much is tan inverse 1? 45 degrees. Tan inverse 2, tan inverse 2, 63 degrees. Okay, 62 point something. So, you interpolate tangent curve. If you know what will be the value between 45 and 63, 45 and 63, it is about 54. So, it will be somewhere close to 54 degrees. Let us take very crude simplification approximation 54 degrees. So, how much is it? Root over of 13, how much is 36 squared? All these square numbers, say root 13 and 1300, the square roots except for the decimal difference it will be same. 1300, square root of 1300, square root of 35, how do you calculate square root of square of 35? 5 square and then 3 into 4. So, 1225, add 135 and 136. So, that gives you 1296, that is 36 square. Next square. So, 1296 is approximately 1300. So, it will be 36. So, 3.6. So, 30 divided by 3.6 and an angle 90 minus 54, okay, 36 degrees, very close to 36 degrees. Okay. So, 30 by 36 is nothing but 5 by 6. So, after a change of decimal it will be 50 by 6, 8.33, okay, and an angle of 36 degrees. Still you can simplify. How much is r plus j x? 36 degrees. If you take it 37 degrees, okay, so that is cos is 0.8. So, 0.8 into 8.33, okay, 0.8 into 8.33 and 0.6 into 8.33 is not 0.6 plus j 0.6, 0.8 plus j 0.6, that gives you approximately 36 degrees. Okay. It is a crude approximation. Anyway, let us put those values. So, that gives me 6.8, this is always an approximation, plus j 4.9. All right. So, for maximum power condition, when you do not have any scope to change the resistance, then I will try to maximize the current, and that I can have RL is fixed, RL is fixed. I am having only XL which can be varied. So, what should be the value of XL? When it perfectly matches with this and there is a cancellation, I get maximum current. So, maximum current under this condition will be 100 volts divided by Ri plus RL, which means 100 divided by Ri was calculated to be 6.8 approximately and RL is 10. So, 100 by 16.8. Okay. 100 by 16.6 is how much? 1.66 approximately 6. So, it will be close to 6, say 5.9 amperes. Okay. So, P max will be I max squared into RL, and RL is 10, whatever be that. So, it is pretty close to say 355 approximately, so many watts, okay, 355 watts. This is approximation. Let us take the second case. and what is the value of corresponding XL? XL should be minus J 4.9, is that all right? Second condition is when you are having XL as minus J 10. So, how much will be the corresponding value of resistance? You are having this is 6.8, this is 5.9, sorry 4.9 J. Okay. Then you are having a reactance, okay, a reactance XL is equal to minus J 10, that is a capacitive reactance, and a resistance which is varied. Okay. So, what should be the condition for getting maximum power here? P is equal to I squared RL, which means 100 divided by how much is the current? 6.8 plus RL. So, if you square it 100 square by this squared plus total reactance which is minus J 10 plus 4.9. So, 5.1 squared, is that all right, multiplied by RL. So, if you differentiate this with respect to RL itself, what would be the condition? dP by dRL equal to 0, you will find after differentiating that this resistance should be equal to the rest of the impedance. Rest of the impedance should be equal to RL, is that all right. So, RL should be equal to 6.8 squared plus this difference, that is 5.1 squared whole thing under root. Is that all right? So, that gives me approximately 8.38 ohms, which is so many ohms. Okay. This is an approximate calculation. All my calculations here will be approximate. So, method is more important. So, P will be corresponding P will be, therefore, how much will be P? 100 squared divided by, now you substitute the values, 8.38 plus 6.8 whole squared plus 5.1 squared into RL, which is 8.38, that comes to approximately 330. Okay. And the last situation is when both RL and XL are varied, and all of you know, because this is the relationship that you normally derive in classes, that is what would be the maximum power transfer to the load. The condition is load impedance should be complex conjugate of the internal impedance. So, RL should be equal to RI and XL should be equal to minus of XI, J is implied. So, P maximum will be voltage by how much is the total impedance? It is RI plus RL, which is twice RI into RI, RI is equal to RL. So, that will be V squared by 4 RI. So, that is 100 squared divided by 4 into 6.8. Is that all right? So, that will be the power approximately 364 watts. Okay. Let us take another example. You will find there is a variety. You might have come across this type of problem. This L is equal to 1 Henry, C is equal to 1 farad. We find that is a parallel combination of 3 such elements. This is 2 Henry to be coupled with a capacitor C1. This is 1/3 farad, 1/3, sorry, let me write it here, 1/3 farad to be coupled with some L2 and another pair L3 C3. What would be these values of inductances and capacitances C1, L2, L3 and C3, such that the impedance seen here and impedance seen here will be same for all frequencies. Okay. That means, this is equivalent to this. Now, if it is equivalent, then under all conditions the impedances will be same. So, I can take some specific values and equate the conditions. All right. Let us see, in general there is a resonance frequency for this impedance, there is a resonance frequency for this, there is a resonance frequency for this. All right. Since all of them, say I can call them Z1, Z2 and Z3. So, Z1, Z2 and Z3, they are in parallel. At resonance corresponding to this, the resonance frequencies are say omega 1, omega 2 and omega 3. Okay. At resonance, and similarly for this the impedance is say Z and corresponding resonance frequency is say omega naught. How much is omega naught? 1 by root L C, that is equal to 1, because L is 1, C is 1, okay, 1 radian per second. Now, this one will exhibit a resonance at omega 1, all right. At resonance, what is the impedance here? 0. So, what is the parallel combination giving me? 0. Any of the arms, if you find that the impedance is 0, that means there is a direct short. So, these two will become redundant. So, the impedance is 0 at omega 1. Similarly, impedance is 0 at omega 2. This is 0 at omega 3, but this is 0 at omega naught. When is this possible? When they are equivalent? Omega naught must be equal to omega 1, omega 2 and omega 3. That means, all the 3 frequencies must be same as omega naught. Is it not? So, if you impose that condition, then what is omega 1? Is 1 by root L1 C1 say. Okay. So, L1 C1 must be equal to LC equal to L2 C2 equal to L3 C3. Okay. So, from the first one, L1 is 2, C1 is to be calculated. So, 2 into C1, LC is 1, we have just now seen, LC is 1. So, that gives me C1 is equal to half farad. Similarly, L2 C2, L2 into 1/3 is also equal to 1 LC, hence L2 is how much? 3 Henry. Okay. Now, if I take a very small frequency, how much will be this? This will be omega into L tending to 0. So, it will be practically capacitive. It will tend to 1 by omega C, if you forget about the J part, because everywhere the J will get cancelled. So, this impedance will be capacitive 1 by C into omega. What about the net value here? This will be short, this will be short, this will be short, omega is 0 practically. So, there are 3 capacitances in parallel. So, C1 plus C2 plus C3, and that should be equal to C. So, C1 plus C2 plus C3 equal to C. Now, C1 is already known, half, C2 is known, that is given as 1/3, and C3 to be determined, and C is 1. So, how much is C3? 1 by 2 plus 1 by 3 is 5 by 6. So, 1 minus 5 by 6 is 1 by 6 farad. Okay. And we also know L3 C3 should be equal to LC, that is equal to 1. So, L3 will come out to be 1 by C3, so 6 Henries. All right. I could have also taken a very high frequency when the capacitors will be short and there will be parallel combinations of 3 inductances L1, L2, L3, and that should be equal to 1. You will find that will also give you 1 by omega L1, 1 by omega L2, 1 by omega L3 is equal to 1 by omega L. So, if you equate L3 will also come out to be 6 Henry in that method. So, either you take a very low frequency or very high frequency and then you equate the corresponding impedance elements. Okay. Sorry. Now, let us take another example. Okay, I will take the next page. You are given, this is a fairly simple network. The values here are in farads, 2 farads, 1 farad, 1 farad and half a farad. Okay. This is equivalently expressed as a star C1, C2, C3. What would be the values of C1, C2 and C3? C1, C2 and C3, how much will be the values? Now, as you know, the impedance of a capacitor is 1 by C into omega. Okay. If we replace these impedances, these capacitances by their corresponding impedances, then it will be proportional to 1 by 2, 1 by 1, 1 by 1 and 1 by half. Okay. So, as if there are resistances, you call it impedance or resistance of magnitude half, just inverse of these 1, 1 and 2. Okay. Now, it is a T network which we can replace by an equivalent pi, that is from a star to delta, then these two elements will come in parallel and then we will get an equivalent T. Once again, if we express those elements of the T network in terms of the capacitances, we will again take the inverse. So, we will get back C1, C2, C3. So, if you just compute, the equivalent of this star, I will just write in one shot, it finally gives me I hope you all remember the relationship between star and delta elements. Okay. You know how to remember? If you want to go from delta to star, suppose this is R1, R2, R3. So, the one which will be in the lap of R1 and R2 will be R1, R2 divided by the sum. Similarly, R1, R3 divided by the sum will be this, all right. And the reverse will be, suppose you are given the star elements, if you want to calculate the delta element. So, suppose this is the element, then the element opposed to this, just opposite of this will be equal to this, from star to delta. So, what should I take? This one plus this one plus this into this divided by this. Okay. It is like R 1 plus R 2 plus R 1 R 2 by R 3. That means, you take the product of 2 at a time and then their sum R 1 R 3 R 2 R 3 plus R 1 R 2 and then divide by the element that will come opposite to this. Okay. So, this one comes out to be 2 by 7, 4 by 7 and 8 by 7. Okay. So, what is the value of C 1? 7 by 2 farads, C 2 7 by 4 farads and C 3 will be 7 by 8 farads. Is that all right? So, these 3 elements are just inverse of these resistances. Next, we go to the computation of 4 terminal network parameters or 2 port parameters. I will take a simple example. Sorry. This is a 5 ohm resistance, this is a 10 ohm resistance, this is 10 ohm, this is 20 ohm, this is 20 ohm. I do not recollect whether we discussed the parameters in the last class with any example. So, what would be this particular numerical problem? We had discussed. Okay. So, we have calculated the parameters Z11, Z22, Y11, Y22. Okay. What would be the ABCD parameters for this? ABCD parameters for this. How do you calculate A? If you remember, what was written as ABCD? ABCD. This was V2, V2 minus I2 and V1 and I1. So, A was V1 by V2 when I2 is 0. I2 is 0 means keep it open, this is I2, this is I1 and I2 is 0 means keep it open, and then measure this voltage, you apply a voltage V1 here, what would be the voltage, and then take the ratio V1 by V2. So, let us see, if I keep it open, the voltage here is this voltage. Now, how much is this voltage? So, before that you have to calculate the equivalent impedance. So, this is 20 plus 10, 30 in parallel with 10. So, 10 into 30 divided by 10 plus 30. So, if I draw a simplified equivalent, this is 5, this is combination of 30 and 10. So, 7.5, 7.5. So, how much is the current? It will be V by 12.5. What fraction of this current flows through this? 20 plus 10, 30 ohms and 10 ohms. So, it will be 10 by 10 plus 30, that is 1/4, 10 by 40 means 1/4 of this. So, if I call it I 2, this is I 1, then I 2 is V by 4 into 12.5. So, V by 50, okay, that is the current here. And how much is the drop here therefore across 20 ohm resistance? Therefore, V 2 will be V by 50 multiplied by 20. So, 2 by 5 into V 1. Okay. Therefore, V2 by V1 by V2 will be 5 by 2, is it not, under open circuit condition. So, similarly you can calculate B, C, D. So, C is also under that open circuit condition when I2 is 0, it is a relation, it is a ratio between I1 and V2. So, how much is I1? I1 means sorry, this is I1, that is the net current that is flowing from here. I should not write I let me call it I dashed. Under the same open circuit condition, how much is the current sent from here, that I have just now computed here, V by 12.5. So, how much is the ratio I1 by V2 under open circuit condition? How much is I1 V1 by 12.5 and how much is V2 is 2 by 5 V1, is it all right? So, V1 gets cancelled, this is 5 by 2 into 12.5, how much is it? This is 25, 5 by 25, so 0.2. So, B is 0.2. Similarly, sorry, this is C is 0.2. B you can compute when we make V2 equal to 0, that is apply short circuit and again measure the voltages, currents from the sending end and the receiving end current. The short circuit current, it will change its direction. So, negative sign will have to be taken properly, you will get the ratio for B and D. Okay. So, I leave it as an exercise to be completed by you at home. I will take another interesting problem with active elements or dependent sources in the circuit. Suppose we have a current source which is 3 times V R2, that is R2 is this element having a resistance value of 20 ohms, R3 is also 20 ohms, R4 is equal to 10 ohms and R1 is equal to 10 ohms. This is 1 dashed, 2 dashed, okay, and this is VR2, assuming this to be plus and this to be minus. The voltage across R2 is VR2 and there is a dependent source, current source whose magnitude is 3 times VR2 flowing in this direction. All right. What would be, say, the ABCD parameters? Now, let us write these nodes as P and Q. Most of the time you will find nodal analysis helps a lot in simplifying the equations and you can get the result very quickly. Let us apply at node P the nodal equations and node Q. What would be the equation here? Suppose this is the voltage V1, this is the voltage V2. VR, this is the voltage Vp equal to VR2, is it not? This is the voltage across the resistance VR2. So, V1, okay, Vp minus V1 by 10 plus Vp by 20, Vp by 20 plus 3 VR2 3 Vp equal to 0, is not, this is the current here. So, if you multiply by 20, so twice Vp minus twice V1 plus Vp plus 3 Vp equal to 0, that gives me Vp equal to in terms of V1, in terms of supply voltage 20 into 3 it is 60, no 3 into 20 is 60, you must be a watchdog, 60 plus 2 plus 1 63 Vp is equal to twice V1. So, 2 by 63 V1. So, this potential is fixed, so long as your supply voltage is V1, this potential is fixed irrespective of whatever you put on this side. It is very interesting. Next, at Q, so current to the current source is 3 times VR2 3 times Vp. So, that is also current source. Okay. This is current dependent current source ICCS. So, I need not write that, ICS is 3 times VR2, that is 2 by 21 multiplied by 3, that is into V1. Okay. Now, if you keep it open, what is V2? We are going to measure V2, the ratio between V2 and V1 to calculate A, is it not, under open circuit condition. So, how much is that? When I keep it open, I2 is 0, I will compute that first. Under 2 dash OC condition, how much is this? How much is this voltage? Current into R3. So, VQ is equal to V2 is equal to 20 into, and how much is that current? 2 by 21 V1. So, 40 by 21 V1. So, how much is V1 by V2? 21 by 40, is it not, and that is equal to A, is not. A is this voltage by this voltage under open circuit condition. Under open circuit condition, what are the measurements that you make? A and C, is it not? A and C will be under open circuit condition, I2 0. So, how much is C? C is I1 by V2 when I2 is 0, and this current by V2. How much is that? How much is that? How much is I1? It is V1 minus this potential Vp, which is already calculated as 2 by 21 of V1, sorry 2 by 63 of V1. So, I1 is V1 minus Vp divided by 10 ohms and divided by V2, and V1 minus 2 by 63 V1. Is it all right? Okay. So, 2 by 61 V1 divided by 63, thank you, 2 by 63 divided by 10 into V2 we have computed as V2, how much was V2? 40 by 21 V1. 40 by 21 V1. So, if you simplify this 61 by 63 into 400 divided by 21. So, 61 by 3 4 the 12 1200. So, this is C. When 2 dashed, this pair 2 dashed, this terminal pair is shorted, 2 dashed are shorted. What will be B? B is minus V1 by I2, is it not? You short this, current flows in the opposite direction, I2 conventionally is positive in this direction. So, I2 is negative and you are applying a voltage here. How much is that? Whether you short circuit or open circuit, this current supplied here is fixed. That is what we found here, is it not? For the node P, we got this equation from where this potential is fixed, all right, and this current, since this current is a constant one, I mean dependent on only this potential potential is a fraction of this potential. So, this current is fixed, it is a current controlled current source, voltage controlled current source. So, this one will be V1 by I2, this is shorted. So, what fraction of this current flows through this side? 20 divided by 30, is it not? So, 20 divided by 30 of this current, which is 2 by 21 V1. Is that all right? So, how much does it come to? 63 by 4. Okay. Similarly, D will be minus I1 by I2, okay. And how much is that? How much is I1? You have already seen I1 is this current, which is V1 minus Vp divided by 10. So, that is what we have already calculated earlier, 61 by 63, is it not? 61 by 63 divided by 10. So, V1 is not divided by 10 ohms. So, that makes it 630 into how much is I2? I2 we have just now seen 4 by 63 V1 just in the previous step. So, that gives me 61 by 40. Okay. So, ABCD parameters we have computed for 4 terminal network with sources, dependent sources. The last one that I would like to take, I think I will stop here. I have another class now. So, we will take it up in the next class. Okay. Before we start the lecture, we will take up 1 or 2 more examples. Thank you very much.
In fact, the same saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shape their mind and body. A collage of events that was a synthesis of competition and cooperation. A collage of interests as diverse as dramatics and ham radio. Yes, life at Kharagpur has always been exciting. And the years cemented lifelong bonds as lives mingled over cups of joy and stretched over stimulating semesters. The halls with their blocks and wings connected by charming catwalks remain ensconced in their own world. A collage of memories. Infrastructurally adequate, architecturally meticulous, and holistically inspiring. Where students, wherever they might be from, invariably come into their own, developing their individual talents, honing their skills to take on challenges with confidence, so they can move ahead in fulfilling their dreams. What makes IIT Kharagpur so unique is its environment. Undiluted by the diversions of metropolitan surroundings, the close-knit campus life enhances the entrepreneurial and innovative spirit of the achievers-to-be. In an environment that is so stimulating, it is only natural that down the years, IIT Kharagpur has consistently produced well-rounded individuals. Many of them are celebrities in their own right. Holistic grooming has had a lot to do with this. So, no matter which walk of life they choose, the IIT KGPite stands tall. And so does the institution that bred him, in majestic splendor. The alumni of this institute command global respect. Their distinguished presence at the helm of global giants is a matter of national pride. For the students of IIT Kharagpur, it is impossible to erase any scratch of memory about their alma mater. In fact, some come back to invest sentiment, pride, and money, to see the institute they call home rise to even greater heights, structurally, functionally, as well as holistically. Their singular aim is to make IIT Kharagpur an institute, whichever way you look at it, par excellence. A man's journey into quiet accomplishment and the Hall of Fame starts with the right step. And the training and placement cell of IIT has been the efficient facilitator in this regard for over 30,000 graduates. Having placed more than 95% of its students in a wide range of industries consistently for over 2 decades, it is no wonder that the institute is the most preferred campus for technical recruitment of quality manpower. With infrastructure like industrial power and communication facilities, in addition to its excellent research and consultancy facilities, STEP, or Science and Technology Entrepreneurs Park, aims to assist the budding entrepreneur into a successful adventure capitalist, guiding him right from the concept, institutional financing, production, leading up to the launch and marketing of the product. With its rich pool of talent and excellent infrastructure, it is no surprise that through the last 3 decades, IIT Kharagpur has developed strong liaison with the industry. SRIC, or Sponsored Research and Industrial Consultancy Cell, was formalized as the Special Industry Interaction Cell in 1982. Devoted full-time to handle industrial projects and consultancies and for deploying and propagating intellectual property. Successful sponsored research projects straddle a wide spectrum, ranging from computers, communication and biotechnology to robotics, photonics and food processing. The setting up of a state-of-the-art VLSI CAD laboratory and tie-ups with GE in areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire. Indeed, in this Golden Jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.